All right, today we're diving into the source materials on a specific piece of hardware, the Thor Broadcast H-RF-MET. It's one of those tools that can save you from those moments of, video flicker and just total dropout. Our mission is to quickly get a handle on why a device like this, a signal level meter, is so absolutely critical for clean, reliable feeds in big distribution networks. Okay, so let's unpack this.
Yeah, that's a great way to put it. This meter is basically your quality control checkpoint for any video feed. It's built to measure cable CATV RF signals, your typical cable, or an ATSC signal from an off-air antenna.
And it covers that huge frequency range, 5 to 870 megahertz. That's key.
It's massive. That means it can handle pretty much everything from, say, older analog FM radio signals all the way up to today's high-bandwidth digital TV channels.
Okay, so when you're installing or even just maintaining a co-sale network, you're always fighting against signal decay, these dB losses. But where do these dreaded losses actually come from? It's not just the length of the cable, is it?
Oh, it's never that simple. Think of the signal almost like water pressure in a really complex plumbing system. Every single time you add a splitter, let's say you're routing the cable to a living room and then to a bedroom.
With a huge drop right there.
A massive, predictable drop. The cable length and its quality cause loss too. But here's the deep dive nugget that people often overlook. The loss rate is totally frequency dependent.
So you're saying the higher the channel number, which usually means a higher frequency, the worse the signal loss is going to be over that same piece of cable.
Precisely. If you're pushing a high-frequency digital signal through, say, hundreds of feet of older, lower-grade coax, the loss on that specific channel can be just catastrophic. Meanwhile, a lower-frequency channel might look perfectly fine.
Which makes just looking at the screen to see if the picture's okay totally impossible. You need actual data.
You must have quantitative data, and that's where the real value of this meter comes in. It's a huge time saver. Well, if you have video problems, you need to know instantly if the issue is a bad signal or a bad TV. Before tools like this, a technician might spend hours just swapping out parts, hoping to find the problem. Now, step one is simple. You check the RF signal, see if the TV's tuner is even getting enough power.
Right, so you can immediately rule out the signal being too low, or I guess even too high.
Exactly. It saves an immense amount of troubleshooting time.
So moving on from the physical challenges, let's talk about signal compatibility. This is where it gets really complex with modern broadcasting. This device seems like it's built to be a kind of global toolkit. It supports almost every standard out there.
It really does. I mean, it handles QAM, which is the standard for digital cable, ATSC for North American over-the-air broadcasts, and even the older analog standards like NTSC and PIAL. So this one tool really bridges decades of technology.
Okay, let's get into the specifics. The source material points out this massive measuring range from 30 dBE all the way up to 120 dBV. For those of us not using this every day, why is that range so important?
That wide scale is crucial. It lets a tech accurately measure the absolute faintest signal from a distant antenna, that's your 30 dBV floor, all the way up to a super high power feed coming right out of a distribution hub, which could be hitting that 120 dBV ceiling.
So it covers the whole spectrum of real-world situations.
The whole spectrum. And with a resolution of 0.5 dBV, you're not guessing. You're getting a precise, repeatable number every time. Plus, it uses the standard 75 ohm F-type connector, so it just plugs right in.
But the real insight here isn't just about raw power, is it? It's about quality.
Yeah.
Tell us about the carrier-to-noise ratio measurement.
This is, I would argue, the most important metric of all, and it's a critical feature on this device. Carrier-to-noise, or CN, tells you about the quality, not just the strength.
Okay, so you could have a strong signal but still have a bad picture.
Absolutely. You could have a very high dBV reading, but if your noise floor is also high, your picture is still going to be garbage. The CN ratio tells you how much usable signal you have compared to all the static and interference. That precise measurement is what lets a technician guarantee a perfect, artifact-free installation.
So to wrap up our deep dives, the HRF-MET isn't just a convenience, it's really a confirmation. The core takeaway seems to be that because of how complex frequency-dependent loss is, you just can't guess. Only a precise tool that measures both power and quality can guarantee a perfect result.
And that need for accurate quantitative measurement is constant, even as the tech changes. You look at the wide range of standards this one device supports, QAM, ATSC, NTSC, it makes you think. If we connect this to the bigger picture, broadcasting is shifting more and more toward IP encoding, away from these dedicated RF systems. So what's the next critical measurement tool going to be? What will we use to ensure video quality over a standard shared beta network instead of coax? That's the next big problem for engineers to solve, and definitely something for you to think about.